Let's say that we start with a random sample, x1 through xn. Remember, by a random sample, we mean that each of these random variables or sample points are independent random variables. Whatever value we observe for x1 doesn't in any way influence the values that I will observe for the remaining x values. It also means that each of these random variables have the same distribution. So they are independent and identically distributed. If all the random variables have the same distribution, they must have the same expected value. So we denote this by mu. They must also have the same variance, which we denote by sigma square. Remember, the expected value and the variance is calculated from the distribution, and if it's the same for all of them, the moments must be the same. The most common statistic is the sample mean, and the sample mean itself is a random variable before the experiment and it's a number after the experiment. So let's focus completely on the before experiment case when x bar is a random variable. Being a random variable, we can figure out its expected value and its variance. If we begin with the expected value, so that would be expected value 1 over n summation xi. 1 over n is just a constant, so I can take it outside. 1 over n expected value summation xi. We also know that I can take the expected value inside sums. So this is 1 over n summation of expected value xi. All of these expectations are the same number. We denoted it by mu. Since the sum goes from 1 to n, the sum becomes equal to n mu. The n cancels, and we see that the expected value of the sample mean is the same as the expected value of each individual random variables in the sample, namely mu. Since x bar is this nice linear function of the x's, it's also very simple to figure out its variance. That would be the variance 1 over n summation xi. Constant goes outside, but for the variance we have to square constants. So 1 over n square variance of summation xi. So in the next step we have a variance of a sum. In this case, all these random variables are independent, so the variance of the sum becomes the sum of the variances. So that's 1 over n square summation variance of xi. So we definitely need the independence assumption, or at least an assumption of the xi's being uncorrelated for this step to work. All the xi's are identically distributed and they have the same variance sigma square. So this is 1 by n square, n times sigma square. We can cancel one of the n's and it's sigma square over n. So the expected value of the sample mean is the same as the expected value of each observation. The variance of the sample mean is not equal to the variance of each individual observation. It is in fact much smaller, and it's smaller by a factor n. We also see that the more observations we have, the smaller will be the variance of the sample mean. There is a lot more to say about the sample mean, but in this lecture I just want to mention one more important property. If my sample is a random sample and each observation follows a normal distribution, so each observation is n mu sigma square, then in addition to finding the expected value and the variance of the sample mean, we can actually find the entire distribution of the sample mean. In this case, the sample mean will also follow a normal distribution. We already know that the expected value is mu and that the variance is sigma square over n. just keep in mind that this is not a general result. So for example, if each observation follow a, say, uniform distribution, then you cannot conclude that the sample mean will follow a uniform distribution. As a matter of fact, it will not. The normal is very special, and the reason that it worked for the case of the normal distribution is that we know that the sum of random variables which are normally distributed will also be normally distributed.